Now we will discuss a widely discussed and a popular algorithm that is associated with the association analysis. It is called a priori algorithm. So as we know, when we want to find association rules in a given database, that is the rules which relate one attribute to another attribute or one item to another item in a list, then we take a two-step approach. First, we want to know all the item sets which have a minimum support. If there is no sufficient support, it is unlikely to be interesting. So that is to say, if it happens so rarely, it is unfair to draw some conclusions, and there will not be enough support for those conclusions. So first we need to identify the item sets which are frequent, and among those item sets we want to generate the rules by partitioning those item sets which tell us that this particular item will lead to another item as per that frequency of that item set, because there we have enough confidence to say that. And it is possible that again those rules have to be validated, but first those rules, to generate those rules, we need to identify the frequent item sets. And identification of frequent item sets is computationally expensive because we need to scan the database many times, and we need to identify the items which are related to each other, and then we check their support in each transaction that we need to scan, and then we need to make numerous comparisons. So we need to find better ways of doing it. So one of the principles that we can apply to improve the process of finding the frequent item sets is a priori principles. So it's very simple. It says that if an item set is frequent, then all its item subsets will also be frequent. It is as good as saying that if there are many transactions which contain bread and milk, there will be many transactions based on some support level. Let's say the support is that 100 transactions per day is your support level. So you are saying that there are more than 100 transactions which have bread and milk. So you can immediately conclude that there are more than 100 transactions which have either bread or either milk, because bread and milk put together you have more than 100 transactions, which is your minimum support. So the a priori principle is that simple. So to express it in a logical terms, for all x, y, if x is a subset of y, support for x will be greater than or equal to the support for y. So this is also referred as an anti-monotone property. So now let's look at how the a priori principle works when we are generating the item sets. Let's say we are generating the item sets. We start initially with the one item set, which is that, let's say we have 5 types of items, A, B, C, D, E. We have probably found the support for that, and then we started combining. We started looking at A, B, then A, C, A, D combinations, and then further 3 items we combined based on what we found with the 2 items, so on. So now let us say at some point we find that AB is not frequent. AB does not have the minimum support. So we know for sure that all the supersets of AB will not have the necessary support. So what does that mean? We can prune these supersets and we have lesser number of sets to work with. So now we look at the a priori approach for candidate generation and testing. Let's say this is the database that is available to us, and we will simply look at it. We need to scan the database for one item set, and then we need to, from one item set, we need to generate 2, 3, 4, so on. And then whenever we go to each item set, we need to see whether it is frequent or not. That is, whether it has the minimum support or not. to formally put it, the algorithm works like this. So it starts with k is equal to 1, generate frequent item sets of length 1, and repeat until no new frequent item sets are identified. So till then you keep performing this loop. So what are you doing? You are generating k plus 1 item sets from the length k, frequent item sets, and there in the among the k plus 1 item sets, since the k frequent item sets, but does not mean that all the k plus 1 candidate item sets are going to be frequent. So you need to do pruning at every step, and then you look at the support for the candidates, each of the candidates by scanning the database. So that is, you are scanning for each time you are increasing the size of the item set, and then you are eliminating the item sets that are infrequent, and so you continue with only the frequent item sets. And at some point you realize maybe when k is equal to 10, you see that there is no item set which has got 11 and got sufficient support. So then you are not finding any new frequent item sets. You terminate the algorithm. So some of the details that we need to work out is that how do we generate the candidates? So what we say is that we start with first scan the database and identify all the items, single items. Let's say in a grocery store like bread, it sells frequently based on our minimum support, and then let's say milk sells frequently. So we find one item, single items, all of them which have got the frequent, which form frequent one item sets, and they have got the sufficient support. And then how do we generate the two item sets from the one item set? So we need to do a self join. So that is, we have got one set which consists of the frequent items where each one item is there. So we are going to do a self joining with this. So suppose A, B, C, etc. there, for example, and here, so you are self joining with A, B, C, and then you know that A doesn't make a difference. So A, B, A, C. A you are joining first with A, and then see that it doesn't add any, it doesn't generate any new subset, new superset, and then you join with B, you're getting a new superset, and then you're joining with C, you're getting a new superset. Similarly, you do with B, C, and all that. So thereby you are getting a new supersets which are one level higher than what you have before. And so what you do is that, and then you're going to look at their count. So now let's see the example. So let's say at 3 item sets, so that is 3 items, 3 item sets. So what we are having is that let's say the items are, here we are assuming that the items that we are considering are A, B, C, D, E. Okay, and then we are seeing that the frequent item sets are A, B, C, A, B, D, A, C, D, A, C, E, B, C, D. So now we want to find out L4. From L3 we want to find out L4. So what do? We join L3B with L3. So thereby we are going to get, for example, ABC and ABD we join, then we get ABCD, ACD, AC we get ACD. So then what we do is that we also look for pruning right here. One is that we can go to the database, scan, and then prune. But it is possible that using the a priori principle we can prune something. For example, we are saying a 4-level item, 4-item set, which is ACD, which is coming from where? ACD, joining ACD and ACE. So now we want to know whether is it going to be a frequent item set. We can use a priori principle and see that one of its subset, ADE, is not among the frequent item sets. So what does that mean? Since ACD is a superset of ADE, it cannot be frequent. So we can prune it right here without scanning the database. So that way when you perform the self join and prune, we will be getting C4, which is ABCD. And after this, having identified ABCD, we still do not know the support for ABCD. We know that ABCD is likely to be a candidate for frequent item set. Unlike ACD, which we know right here that it is not a candidate for frequent item set. So we need to think of finding the supports. So now let's take the a priori principle and let's apply the algorithm with a real item set. And what we have done is that we have a database which is given here, and from this we scanned the database and found one item sets. So we have seen and found that bread is existing in 4 transactions, so it has a count of 4. Similarly, you can do for everything else. And we decided that the minimum support is 3. So what does that mean? We are clearly removing the items which do not have the minimum support. And now we are doing a self join among these 4 item set: bread, milk, butter, diaper. So all of them have minimum support, and if there is to be any 2 item set which will be frequent, that will only come from these 4 items. So then when we combine that, what we get is that there are 4 items, so we can create 6 combinations. Okay, and then from those 6 combinations we look at their count. So for this we need to scan the database again, and we get a count which is we can get by scanning. So bread, milk, we can see that it's coming in 1. This is 1. Just for an example, we'll do that. Bread, milk is happening here, and bread, milk is happening here, and bread, milk is happening here. So we put a count of 3. So the same thing we do for all the combinations. And now we realize that this is not frequent anymore, and this is not frequent anymore. So again, we have got 4 2 item sets. They have got the minimum support, so we consider them as the frequent item sets. And now we want to find out the triplet, so that is the 3 item sets. And we do the same thing. We do a self join, and we are going to get numerous 3 candidate item sets, and among them we will find that only bread, milk, diaper, which is coming from bread, milk, diaper, we do not have the bread, milk, diaper is existing only in 1 and 2. So we will realize that only so this is also not frequent. So in the sense that we are finding a potential candidate item set, and this candidate item set does not have the sufficient support. So at this point we can stop. So all other item sets we had eliminated because their subsets are not frequent. So for example, we take bread, milk, and then milk, diaper. Okay. Okay. So bread, milk, and then we will look for, let us just wait for 1 minute. Bread, diaper, butter, diaper. So both are frequent item set. So now let us say we will form one bread, then butter and diaper. So now we start looking for, is this diaper, butter existing? It is existing. Diaper, bread is existing. Butter, diaper is existing. And then bread, diaper is existing. Bread, diaper is existing. Then butter, diaper is existing. Then, okay, bread, butter is not frequent. So what does that mean? That means that we can prune it even without scanning. So that way we end up with only this one single item set, which is not pruned without scanning, but this one gets pruned after scanning. So that way we can stop the algorithm at this point. So since for this the count is 2. So now we'll see how to count the support of candidates. See, the number of candidates can be very huge. We looked at a very small database, and still we can see that the combinatorial number of the candidates is high. If you look at here, in general, the number of subsets will be, since we are going from up to 3 levels, so 6C1, 6C2, 6C3, the summation will lead to 6C1 is 6, 6C2 is 15, and 6C3 is going to be 6 into 5 into 4 by 3, so which is equal to 20. So that is equal to 41. But with the help of support based pruning, what we ended up is that here we looked at 6 items, and then we pruned, and then we looked at 6 items here again, and we pruned, and we proceeded here, and we ended up with only 1 item for which we needed to do a comparison by scanning, and then for that also we find that it is not, so we are stopping the algorithm here. So instead of 41 subsets for consideration, we considered only 13 subsets. And how did we achieve this? Simply using the a priori principle. So when we are making a comparison of each transaction to see whether it is adding to the support of one of the candidate item sets, what we are doing is that we are reading each transaction and we are making comparison with the entire set. And as we see, that set can be large for when we have the large number of items. So there are techniques whereby instead of comparing with all the candidate item sets, we only compare it with a smaller number of candidate item set. Thereby we improve the performance of the algorithm. So how it is done is that with the help of a hash tree. So how does that hash tree look? What we do is that suppose we have this many candidate item sets at level 3. So this is what, this is happening is that 1, 2, 3, 5, 6, 7, 9, 10, 15. So we have got 15 candidate item sets. And then how many items do we have within that? It is from 1 to 9, let us say. And then what we do is that we also assume that all the transactions are organized in order of the item set. So that is items. So if there are items 2, 3, 4 are occurring within a transaction, the transaction will be represented as 2, 3, 4. Not as a 4, 3, 2 or 3, 4, 2. So that way it will help us in making the comparison and organizing the hash tree. So now what we do is that we divide hash using a 3 function, so modulo 3 function. So what we get is that on the left branch, we will have at each node maximum of 3 branches in the tree. And so in the leftmost branch, we take 1, 4, 7, and in the middle branch, we take 2, 5, 8, and in the right branch, we take 3, 6, 9. So when we get a candidate item set such as which starts with 1, so it is going to be going into the first branch. And then at this point, again we look at what is the second item. Second item in this case is 3. So we made it traverse through the third branch. And in this case it is 4. So we made it traverse to the first branch. So here, as you can see here, again this is third item is going to be again 4 or 7. It traversed at the third level also, it is going to the leftmost branch. Same thing we do here. Here this is an item set starting with 2, so it is going into the middle branch. The item set starting with the 3, it is going into the third, the rightmost branch. And within here, if the next item is 4, so since the 4 should be going into the leftmost branch, at the second level it is going to the leftmost branch. And then the second item, when it is 6, we know that it should go to the rightmost branch, it is going into the rightmost branch. So we have organized the hash, all the candidate item sets in the form of a hash tree on the modulo 3 principle. So the tree will expand to the same number of levels as the number of items within the item set. So if you have got 4 items within the item set, then it can go up to the 4th level. And now what we will have to do is that we have to use this tree for making comparisons and see how it helps. So just for the sake of completeness, we will see when it is 1, 4, 7, you can see that the item sets which are impacted are these 2, because that is determining that the path through which it is going to reach. And if it has got 2, 5, 8, it is being determined by this path, the middle path here, the middle path here, and the middle path here. And 3, 6, 9, it is the right path here, right path, and then the right here, this path, and then in here, right here, this path, and here there are no subtree. So no branches, so there is nothing to check. So now let's say we have got a transaction which is 1, 2, 3, 5, 6. And one thing we know is that all the item sets are ordered in the same sequence, and the transactions are also ordered using the same sequence. So now we know that any transaction, any item which is starting with 1 has to be found only in this branch of the tree. So we are dividing it into 1 and 2, 3, 5, 6. And so what we will do is that we look for, since there is a branch, that means that there are some item sets which start with 1. So what we do is that now our problem is reduced to finding 2, 3, 5, 6 in this subtree. So we'll go down further and we will see that whether 2 can be found and then 3 can be found, and then based on that we make the comparison. And then when it comes to the middle branch, we know that the 1 has been taken care using this subtree. So we don't need to worry about having 1. So we will look for the item sets which start with 2. So since this, we are coming to this branch, so the 2 is there, and then whatever item sets are there, we should check for 3, 5, 6 presence there. And similarly in this side, we don't need to worry about 1, 2. We start only with 3, and then the items are 3, 5, 6, and we look for that within this subtree. So when we do one step further, this 1 we are going further because 2, 3, 5, 6 has to be found. So for going here to the middle root, we'll say 1, 2 we separate and we look for 3, 5, 6. And this is not to be worried because there is nothing with 4 here in this, and nothing with 7. And then we will start with, because 1, 2 should be found in this subtree. So we will not worry about 2 also. We will look at 1, 3, 5, 6. We will look for this subtree for that. And then having come down, so we look for 1, 5. It can also be in the same subtree into which you are looking at. So 1, 5 plus 6 also, if it exists, it is going to be in this. So this one and this one has to be checked in this path as a children of this, and then this one has to be checked along this path. So now we have got a specialized paths for looking for each subset. So thereby we can avoid some of the comparisons. We saw no need to worry about this path at all. So that way we are going to get, for example, 3, and then we have only 5, 6, so we don't need to go through this path. So we are eliminating some of the paths. So what that means is that we are eliminating some of the comparisons. So now we can look at we can see that we needed to visit only 5 out of the 9 leaf nodes, and we needed to make only 11 out of the 15 candidates for comparison. So thereby we are improving the efficiency and we are doing lesser number of operations before we are generating, we are identifying the support, and we are looking for the frequent item sets, because all these are the candidate item sets, and only after we find the support, by comparing with them with the transactions, we will know whether they have the minimum support to become a frequent item set. So some of the factors which affect the complexity when we are finding these frequent item sets is that the minimum support threshold. The moment we say the support is low, we are going to end up with many more frequent item sets. So thereby we will have the more candidates and more comparisons. And if there are more types of the items, then there is a possibility that we need to generate more subsets. And also we need to provide space for storing the count for each one of these items. And then so thereby the computation and IO cost can also increase. And if the size of the database is big, we need to scan the database many times, so the time for the algorithm will increase. And if the average transaction width increases, then that will increase the length of the frequent item set. So that means we need to do more traversals of the hash tree. And then as we are finding more and more frequent item sets, we need to keep scanning the database again and again. Now let's look at 2 associated concepts. One is called closed pattern, closed frequent item set, and maximal frequent item set. So that these are the specific terms that are used, and sometimes we look for this type of patterns. So we may have a long pattern which will consist of a numerous sub patterns, but instead of mining all the sub patterns, we will only mine for the closed or the maximal. That will give us significant insight. We consider a item set X as closed only if X is frequent and there is no superset such that X is a proper superset of Y with the same support as X. So what it means is that Y may be frequent but with a lesser support than X. And in item set X is considered maximal if X is to be frequent, and then the superset Y should not be a frequent. So here we are not talking about support, we are considering only if it is frequent or not. So now let's look at an example. Let's say we have got a database which has got just two transactions. One transaction has got 100 items and another transaction has got 50 items, and we decided that the minimum support is 1. So what is the number of closed item sets here? So we are going to get 2 because the minimum support is 1. So A to 50 is we are getting a support of 2, and then A to 100 we are getting a support of 1. So now we are saying that when we are looking for the maximal patterns, we will only stop at this because this is frequent, so we don't need to look at this. Because this we looked at because its parent did not have the same level of support. But now here we are only looking at, because both are considered frequent, so we will only consider which is the maximum. But then if we want to look at all the subsets, how many subsets we are going to get? We are going to get approximately 2 to the power of 100 possible subsets because there are 100 items. So when we calculate, we are going to get approximately this number. So now just to take an example to look at how this works, suppose that we have 5 transactions where items are A, B, C, D, E, and we start looking for the support for each one of these items. For example, A is occurring in 1, 2, 4 and D is occurring in 2, 4, 5. So we mark like that. So we start building the graph. And then from A, we can go to its supersets A, B, A, C, A, D and all that. And then, so we can do the same thing, and then we can find the supporting transactions for each one of them. And then once we reach the A, B, C, D, E, we see that this and this, there are some combinations for which there is just no support. So we are not concerned about that. So now we want to find out which are maximal and which are closed. So when we are looking at closed, let's say we looked at the minimum support as 2. So when E is having a support of 3, and when you look at the supersets of E, what are the supersets? AE, then we have BE, CE and DE. When you look at AE, it has support of only 1, BE is 1 and CE is 2 and DE is 2. So that means CE, DE are frequent, and AE and BE are not even frequent. But now what happens is that we are looking at this is closed because its parents do not have the same level of support as its supersets do not have the same level of support as E. But when you look at maximal, you are only ending up with 4. So what happens is that we have 9 closed frequent item sets, but only 4 maximal frequent sets. So if we are concerned about the maximal frequent item sets, then we need to consider about a very small part of this graph. So we are only considering the 4 item sets. So if we create a set diagram that will somewhat look like this, among all the frequent item sets, some of them are closed frequent item sets, and among them only some are maximal frequent item sets. And there are some alternative techniques that people use for frequent item set generation, which they do is one thing that they try is changing the representation of the database. And instead of representing as individual transactions and for each transaction representing the items, they represent each item and identify the list of transactions in which it is part. Thereby you are getting the support level quickly. And then you do not need to, as you can see here, if you want to find the support for AB, you need to scan this much of database to find the support for AB. And for finding support for AB, you need to scan this much of database. As you can see here, the size of this, what you are scanning, if you consider the page size and the number of pages to be read and so on and so forth, that will turn out to be less when you create a vertical data layout. So some people prefer to use this vertical data layout for frequent item set generation.